Okay, so everything is recorded now. So now, so maybe let me start with question number 1. Okay, so now question number 1 is how do you define those matrices A, B, C, D. Okay, and then we start with matrix A. So how do we define the matrix A? So maybe let me. So I assume that you have Matlab with you somewhere, the online version or the one on your laptop. Okay, so I will start typing the commands. So suppose I go to my Matlab. So now wait a second. So let me make my Matlab visible to you. So let me share my Matlab screen. Yeah. So you see that we start with question number 1. Yeah. So now let me share my screen. So please ask question in the chat if you want to ask question. Yeah. So now let me share my Matlab screen. Okay. So you see my Matlab screen. Yeah. So now you can, create a new script. So because you can play with the command windows directly, or you can make a new script, because it's better to make a new script so then you can have a records what you have done. Okay, so the new script will be, say, like suppose you say that, okay, so this one is question number 1. Yeah, and then part I. Okay, so now you define the matrix A. Okay, so the matrix A has the size 100 by 200, and every elements are 1. Okay, so you have a commands called ones. Every elements in the matrix will be ones. Yeah, and then you give the size of the matrix. So the size is 100 rows by 200 columns. Okay, so this is how you define the matrix A. Okay, and now how do you define the matrix B? So the matrix B is just, all the entries are 2, 2, 2, 2s. Yeah. So how do you define the matrix B? So anyone, can you type in a possible commands? Yes. So 2's multiplied by the matrix A. Yes. Okay. Because it's the same size of the matrix A, and every entry is just 2. So you can divide just 2 multiplies by A. Okay. So A are just ones, 1, 1, 1, 1, 1. 100 by 200. Yeah. And then the matrix C. Okay, so now, so this is part 2. So how do you define the matrix C? How do you define the matrix C? So maybe let me save the script. So they ask you to save, and you save as maybe week 1, week 1, 2022. Okay, and you see that it's like 1 to 60. Yes, you can do that, but well, I mean, we can try, you know, but suppose you put a open parenthesis like this, okay, then I mean, you can give the beginning and the end, okay, and the beginning and the end is 1 and the end is 5, and if there's no increment, then it gives you from 1 to 5, okay, and if there's an increment, you know, like suppose you put 119, well, so the increment could be a negative number, okay, and if it's a negative number, then it decreasing, you know, from 119 to 1. Yeah, so the matrix C, as you said, is correct. Yeah, so you can define like the first row is just 1 to 60. Okay, and then the second row is 119, going down by -2. So increase by -2 means that going down by 2. Yeah, and stop at 1. And the last row will be from -3. So every step increase by 3 and stop at 174. So you see that if you run this script, okay, you hit the button run here, you can have A, you can have B, and you can have C. Yeah. So this is a matrix C. And now how do you get a matrix D? How do you get the matrix D? So how do you get the matrix D? So what is the pattern for the matrix D? So how do we get the matrix D from well, the hint is D, you know, is obtained by matrix C. You just swap a few rows. So there is no particular formula for the matrix D. Okay, so matrix D is obtained from matrix C by swapping a few rows. So that is the hint. So how do you do that? How do you obtain matrix D from the matrix C? Anyone? Can you type in the chat box? Yes, you are correct. Yes. So essentially the matrix D, you just take the third column of the matrix C, right? And the fourth column of the matrix C, and the first column of the matrix C, the second column, and after that everything is the same. Yes. So you know, Kato Yamai is correct. Yeah. So now I can put it in your command into my Matlab. Okay, so you get the idea, right? So this is your matrix D. And the column means that on the rows. Well, if it's in the first, in the first index, then on the rows. But if in the second index, then it on the columns. Okay. So if you write C1 columns, it means that on the columns. But if you want on the rows, then you write C columns and then say 3. Okay. So then if you run it, then you get the matrix D is exactly like we have here. So 3, 4, 1, 2, 5, 6, and so on. Okay, so that is matrix D. And then now the third one will be a vector. So now how do you define a vector? How do you define the vector? X equal 1, 2, 4, 8, 16. You see what is the pattern? So 32 and so on, and it stopped at A192. So how do you define the vector X like this? And again, you can do it in one line. I mean, somebody said that, okay, use a loop, but I mean, Matlab allows you to do a lot of vectorized commands, so you can do this in one line. So anyone, have you look up the manuals for Matlab? Okay, so if you cannot do it in one line, then how do you do it? You use a loop, or you use a loop? Yeah, but see, we can do it in one line. So you see, this is the loop. The loop is correct, but in Matlab, I mean, is very famous for vectorized commands, and vectorized command will be carried out faster than the serial command. Okay, so Matlab make use of parallel processors, and vectorized commands will be much faster. This is correct, yes, but we need only one line. So okay, so think about this. So now what is the pattern? So you see the pattern is every entry is 2 to the power of an integers. Okay. So now let me go to the command windows, and I can play around with the vectors. Yeah. So suppose I put in just the power, right? So the power is, you see, the first one is power 2 to the power 1. Okay. So, and then the second one is 2 to the power 2. And sorry, the second one is 2 to the power 1, and 2 to the power 2, 2 to the power 3, and so on. So what is the last power? So the last power is 2 to the 12. No, sorry, 2 to the 13. Okay. So the last power is 13. Yeah. So you see that the first power is 0. Okay. And the last power is 13. Okay. Yeah. And then now if you raise 2 to that power, okay. And again, because I want to take on the elements inside the vector, right? And then raise to the power. So I use this operation. So I use raise to the power, but with a dot in the front. So it means that it will carry out element wise. Yeah. So take 2 raised to each element in this vector, and you see that it gives you the correct results. Okay. So this is the command. Yeah. So 2 raised to the power from 0 to 13, and it gives you exactly the vector x. So it's only single line. Yeah. So you see, if you use a for loops, then it is correct, but it will be slower in MATLAB, whenever you try a vectorized commands, it will be faster. Okay, so that is the unique features of MATLAB. So then, okay, so the next one will be a related vector. So this one, suppose I have y is 1, then minus 2, 4, minus 8, and so on. The last one is minus A192. So how do you define the vector y using the structure of the vector x? How do you define? How do you define the vector? Yes, so minus 2. Yeah, it's correct. Yes. So y will be minus 2. Yeah. So you just put minus 2. It's very good. So you got the idea, right? So now if I put, instead of 2, I put minus 2. Okay. Then you run it. So you see that y has exactly the structure. Okay. So that is question 1 and question 2. Okay, so somebody asked me how you run only a section. So you can run a section like this. So question 1, yeah, is we just end the section here. So we call it this question 1. Yeah. And now we go to question 2. So how do I make a new section? Maybe maybe later. But right now, maybe let me just make question 2. Yeah. Okay, so question 2 is, now you have a matrix A and a vector B. Okay, so now I have a matrix A is given by minus 5, 0, 3, 1. This is the first row. And the second row is 4, 3, 6, minus 1. And 3, minus 5, 2, 0. And 2, 2, minus 1, minus 4. So this is my matrix A. And I define the column vectors B, 11. So there's a column vector. So every element in the vector is separated by a semicolon. Okay. So 17, minus 14, and then 2. Okay. So sorry, this one should be a vector B. Yeah. And now I use the linear. I use the backslash operator to solve the linear system. So solve AX equal B. Okay. So you just solve A backslash B. So what it means is it will do the Gaussian elimination, okay, to solve AX equal B. So this is a backslash command. Okay. So it's equivalent to say that it is the inverse of A multiplied by B, but it didn't compute the inverse of the matrix, because it's not a numerical stable algorithm, but rather it solves AX equal B by Gaussian elimination. Okay. And now we can run only this part. Okay. So now I run only this part. So run. So then I have x. So x is a vector of the solution ax equal b. So -1, 3, 2, and 0. Okay. And now find the eigenfunction of find the eigenfunction and the eigenvectors. Sorry, eigenvectors and eigenvalues of the matrix B. So how do I so how do I find the eigenvalues and eigenvectors? So this one is part I. So this one part double I. So the matrix B is defined to be A transpose A. So A transpose, you know, is you can use a prime for. So this one is only for a real matrix. So real matrix, when you take a prime, it means it's a transpose. Okay, because if A has complex entries, then what the prime does is it take the transpose and the conjugate of the complex numbers. But so suppose that the matrix A has real entries, then this one just take the transpose of the matrix. Yeah. And then we find the eigenvectors and eigenvalues. So there's a command, you know, give you eigenvectors and eigenvalues of the matrix B. So now verify that the answers from part I and part double I is correct. Okay, so now how do you verify that? Well, you can verify, how do you verify that X is a solution of AX equal B? So how do you know that AX equal B? So remember we solve AX equal B, right? But now how do we know that X is a correct solution? Any ideas, any suggestion, any comments? So how do you show that X is the correct solution of AX equal B? And secondly, how do you show that, you know, the eigenvalues and the eigenvectors are correct? Anyone? Any? Maybe do the first part first. How do you show that AX equal B? Yes, you take A multiplied by X and then what? Exactly. Okay, so that is a very good point. So now you can take AX, right? And you multiply AX and check whether it's equal B. And then you see that B is 11, 17, minus 14, 2. So it's correct, yeah? So when you try to compare the two vectors, yeah, you can see that AX minus B, okay, give you a zero vectors. And we will cover in the lectures tomorrow that, you know, in Matlab, you cannot have a absolute zero, but it will be like 10 to the minus 14. Okay, then 0, 0, something very close to 0, but it's not absolutely 0, but very small number, 10 to the minus 14, you know, multiply with something, yeah. Okay, so that is how you verify the solution AX minus B, yeah. Or you can find out whether a vector is a zero vectors by the command called norm. So again, we will cover this in the lectures in week 3. Okay, so norm of a vectors, when it's a very small number, then it's a zero vectors. Okay, so you can say norm of AX minus B, if it's a zero vectors, then then it is a correct result. Okay, so now for the eigenvalues and eigenvectors, so how do you check? So remember, so now if I display what is V, so V is a set of eigenvectors, and D is a diagonal matrix that give you a diagonal values, which are the eigenvalues of the matrix B. So now how do you check that those are the eigenvalues of with respect to the eigenvectors of the matrix B? So what does it mean by the eigenvectors and eigenvalues? Anyone remember your first year algebra? So what does it mean by eigenvectors and eigenvalues? Okay, so let me remind you, what does it mean by the eigenvectors and eigenvalues? Okay, so suppose, so now let me try to draw a picture. So now how do I draw a picture? So let me try to draw pictures. I will remind you what is the eigenvalues and eigen. Okay, so let me draw pictures. Yeah. So you see, I mean, suppose you have a vector x like this. It's a very bad drawing, but anyway, so go back. Okay, so suppose you have a vector like this. Okay, so yeah, and then when you, there's a chart, yeah, eigenvectors, yes, AV equal lambda V when A is a matrix, yes. It doesn't change the direction, yes. Now it's a correct, yes. So it doesn't change the direction under the linear transformation, yes. So the correct formula is AV equal lambda V if A is a matrix and V is eigenvectors, yes. Okay, so that is what I'm looking for. So AV equal lambda V, you see, when you apply the, so suppose this is a vector V, right? When you apply to a matrix A, right? So you multiply AV, then it doesn't change the direction. So this is the lambda V. Okay, so AV. So that's what it means. Yeah, so AV equal lambda V. So it means that you apply the transformation to the vector, it stay in the same direction, you know, just different by scalar. Okay, so now go back. That is the one I'm looking for. The formula is AV equal lambda V. Yeah. So now how do you check that? So now, you know, remember now we find the eigenvectors of the matrix B. Yeah. So what I want is I want B V. Okay. So now what is V? So V will be, remember, the column of the first the first column of the matrix V is the first eigen vectors, okay, and then it should equal the eigenvalues. So the first eigenvalue, so D11, okay, so the first eigenvalues multiplied by the first eigenvectors, okay, and then because you wanted to see whether it's 0 or not, so you check, okay. So this one is like, maybe I should give some comments here. Checking whether ax minus b is a zero vectors question. So there's a chat. I can't see your screen. So what do you see? So sorry, maybe I have to. Is it better now, or maybe let me put it here? So maybe let me share the screen again. Yeah. So is it better now? Okay, thank you. Okay, so just okay, so now, you know, so this one is checking ax minus b is a zero vector, and this one is, so I have to scroll down a bit. So checking the first eigenvectors, eigenvalues. Okay. So BV, so BV minus lambda V. Yeah. So lambda is D11 is the first eigenvalues. Okay. And the first columns is the first eigenvectors. And then now if I run it, I run a section. Yeah. So you see that, you know, the answer is 10 to the minus 15. So it's very close to zero. So it's correct. Yeah. And you can do the same for the second and the third. You can do the same for the second and the third. So this one I just want to cut and paste or make it faster. Yeah. So this one is the second, and then the third. So this one is the second one. Well, but now the second eigenvalues is the second in the second entries in the diagonal matrix. Okay. And then you do the same for the last one. So this is the third. So the third eigenvectors, eigenvalues. So this one is the last entries in the diagonal matrix. Okay, so now we save it and we run it again. So we run the section on the section for question 2, and you see that, you know, you see in the command windows, you see like 10 to the minus 15, so it's very close, 10 to the minus 14, so close to zero. So what Matlab does was correct. So it computes the eigenvalues and the eigenvectors correctly. Okay. And now the next part is find the eigenvalues of vectors A. Okay, so now finding eigenvalues of A. Okay, so now, you know, if you want only the eigenvalues, so you can have, you know, only one output of the EIG command. So EIG, when it has two outputs, then it finds the eigenvectors and the eigenvalues. Okay, but when you use only one output, then it gives you only the eigenvalues. Yeah. So now if I run this, so I run the section. So you see now, because I didn't display lambda, but if I ask what is lambda, so then it gives me a list, it's a vectors of 4 eigenvalues. And you see that the eigenvalues of the vector A could be a complex number. Yeah. But the complex number, I mean, one has two real values and it has two complex values, and the complex values are conjugate of each other. Okay, so at least for this case. And now verify that the product equals the determinant of the matrix. So there's a command from product. So it will take the product of the eigenvalues. So product of eigenvalues equal the determinant of the matrix. Why the eigenvalues are complex again? Well, in general, you have a real eigenvalues if you have a symmetric matrix. But this matrix is not a symmetric matrix. So you can have a complex values. Okay. So that is a fact in linear algebra. So linear algebra say that if you have a symmetric matrix, then all the eigenvalues are real numbers. But here we don't have that case. So here A is a very general matrix. So you can have a complex eigenvalues. Okay. And so this one is another theorem in linear algebra. So again, so what I mean is in this, you have to revise your linear algebra because Matlab, just do all the computation which is consistent with what you know in linear algebra. Okay, so otherwise, because linear algebra is a ground truth, yeah, and Matlab is just a tool, and it will evaluate everything numerically. But I mean, it has to follow what is known in linear algebra. So this one is another theorem in linear algebra. So is there a way to tell just from the eigenvalues? If you didn't know what A was, how can you find the eigenvalues? So the eigenvalues depends on the matrix A. Okay, so in general, the eigenvalues could be complex numbers.
Sorry, I'll just unmute myself for a second if that's okay.
When A is a symmetric matrix, then there's a theorem say that all the eigenvalues of a symmetric matrix are real numbers. Okay, but in general, they are complex numbers. Yeah. No, I cannot hear you. I just.
Oh, okay. Never mind. I'll type my question in the chat.
So I just see your question from the chat. Okay, so everything is okay, right? So now we can go on, yeah. So now let me continue with the next part. So now the product of eigenvalues is a determinant of the matrix. So this is another theorem in linear algebra. Okay, so we want to see that whether the product of the eigenvalues equal the determinant of the matrix A. Okay, so this one is the command, just compute all the eigenvalues. I mean the product of all the eigenvalues stored in the vectors lambda. Okay, lam. Yeah, and this command that I just compute the determinant of the matrix A. And now if I run this, and you see that the product of the lambdas, I mean of the eigenvalues equal the determinant. So answer just equals 0. Okay, so this one is another results in linear algebra could be verified using Matlab. Well, it's not a proof. Okay, I mean if you want to prove a theorem, it's another story. But this one just shows that Matlab is consistent with what is known in linear algebra. Yeah, so the theory is stronger, and this one is just a special case. When you show the special case, doesn't mean that you prove the theorem. Okay, so that's why we need a theory. Yeah. So that is question number 2. So any question about number 2? Any question about question number 2? So far so good, right? Okay, so question 2 is done. So now question number 3. So question number 3. So now write a script. So how do you write a script to do the following thing? So first, you build an upper triangular matrix of dimension 12. Okay, having 4 on the main diagonal and -2 on the upper diagonal. So how do you build the upper triangular matrix of dimension 12? Okay, and having, so this one you can use a for loop, but it's not recommended. Okay, so it's recommend you to use the vectorized commands from Matlab directly. So now how you build the upper triangular matrix of dimension 12 and having 4 on the main diagonals and -2 on the upper diagonal. So you see that. So what does the matrix A look like? The matrix A look like this. So A will be 12, yeah. Okay, and then, sorry, it has 4 on the main diagonal and -2, and then 0, 0, 0. You know, how many zeros you have? So you have 10 0, yeah. 1, 2, 3, 4, 5, 6. 8, 9, 10, yeah. Okay, and then the second row will be, 0 here and -4 here. Sorry, 4 and then -2 and then 9 0. Okay, so you get the idea, right? But did you mention whether it would be sharing this Matlab document with us on Moodle? So which one? The Matlab documents, which one? You mean the reference? So did you read the lecture notes? The lecture notes is on Matlab, the chapter 1. It's on Moodle already. So you mean the solution of this lab, or solution of this lab will be posted after the lab? Okay. Solution of the lab will be posted after the lab, yes. But you see, in the lab, I want you to play around with Matlab so that you can learn it faster. Because you read the solution, you might think that you understand it, but it's better you play around with Matlab and during the lab you can try to practice on the fly. Okay. So now, but this one, the problem with this solution is correct, but it's not automatic, because suppose I increase the matrix size to 100, then you don't want to type like 98 zeros, or I increase to 1000, you don't want to type 998 zeros. Okay, so this is not a recommended solution. So now in Matlab there is a command like diagonal, and it will give you the diagonal matrix. So suppose I put in diagonal, put in a vectors 1, 2, 3 like this. Okay, and it gives me a diagonal matrix from 1, 2, and 3 on the diagonals only. Okay, so now suppose I put in, say, from 1 to 12, then it gives me a diagonal matrix, all diagonal entries are from 1 to 12. Okay, so you see, for diagonal matrix, then it's very simple. Now what happened is I want the upper upper diagonals, right? Because you see the question say that I want the -2 on the upper diagonals, yeah. And now there's another command. So now I don't remember the commands, but suppose I forgot and I said that help diagonal, okay. And you see that they have so they have a help here, and you can see that diagonal can take the next input, yeah, and the next input can somehow allow you to move the diagonal up or down, okay. So now let me try to play, say, diagonal 1, 2, 3 again. So again, you see, during the even the Matlab test, you are allowed to use the reference. You can use Google, you can use whatever. You don't have to memorize the commands, you know, but you have to remember roughly what the command will do before you look it up, and you can try it on the command windows. So now suppose I put diagonal 1, 2, 3, and I put the -1 in the second input, then what it does. So what it does is now you see that instead of 1, 2, 3 on the main diagonal, now it moves down to the lower diagonal. Okay. And now if I do +1 and it moves up, you know, the upper diagonals. Okay. So now you use this command. How do you construct the matrix A again? So now how do we construct the matrix A? So this one is go back to part I. So I show you the commands already. Just use the diagonal commands and you can construct the matrix A easily. So now anyone? So remember the matrix A is upper triangular matrix, but actually it has only the diagonal, the main diagonal are equal 4s, all of them 4s, yeah. And then the upper diagonals are just -2. So now how do you use this command diagonal with a vector, and you can move up, move down the upper and lower diagonal. And now how do you construct the matrix A? Anyone? The question means the whole upper part. No, not the whole upper part. It's just -2 on the upper diagonal. So upper diagonal is exactly like here. So the upper diagonal is, in this case, it's just 1, 2, and 3. Okay. So only, not the whole upper part, but only the upper diagonal, -2. Upper diagonal. So this one, you know, this matrix has only two bands. Yeah, one is the diagonal bands, what are equal 4, and another one is the upper diagonals bands, and they are equal -2. Yes, it's correct. Yes, so this is the correct solution. So you can say that 4 multiplies by a vectors 1, yeah, and then so on the diagonals are 1s, yeah, and then you have upper diagonals just -2. So you can run this, and so run this section and you will see the, oh sorry, I have a extra, right. Okay, so you see this is the matrix A. You see that. So all the diagonal entries are 4. Okay. And then all the upper diagonal entries are -2. Okay. And now, so this is a matrix A. And now I can create the part. So you see, I mean, you can use a for loops, but for loops are not recommended in this case. So Matlab provided a lot of special commands to construct special matrices, and diagonal matrices is a special command like this. So matrix B are the matrix A, but the second and the 10th columns are interchanged. Okay, so now you should know how to do this. So maybe let me do it, so the second and the 10th columns interchange. So you say that this one is A. So we have the first column here, and the second become the 10th column. Okay, and then you have A. So 3 to 9, and you got the 10th column here, and then you got all remaining columns. Okay, so this one will be 11 to n, and this one gives you a matrix B. Statement is incomplete. Hold on. I forgot to close the. So the matrix A is like this, and matrix B like this. Okay, so you interchange the second with the 10th columns. Okay, and then you can swap the 4th and the 9th rows. Okay, so this one you can swap the rows as well. So the matrix C will be swapping the rows, so the 4th and the 9th rows. So you got 1, 8, 2. Sorry, which one? In B after 3, 9. Good point. Yes, thank you. Sorry, this is a second column. Yes. It has to be a second column. Thank you. Yes, thanks a lot. So you are paying attention. Yes. So we swap the 10th with the second columns. Yes. So we have to do this. Yeah. Okay. Thank you. So it's good. So now you can do the same for the matrix C. Yeah. So I guess we cannot do everything. So now let we well, maybe let me so I leave question C for you. Yeah, but now let me do question 4 real quick. So sparse matrix. So sparse matrix is again a special matrix that you have a lot of zeros. Okay, and you don't want to waste memory. So in Matlab there is a command called sparse. It will create a sparse matrix for you. Yeah. So now suppose you help sparse, then it gives you the description. Okay, so now you can convert a sparse I mean a full matrix to a sparse matrix by this command. Yeah. So now you can define a sparse matrix, okay, from this command, or you can have you know, sparse ones matrix, sparse identity matrix. Okay, so in this case we have only so I just do a simple one. Yeah, so now suppose I do A is a full matrix first, so 0, 7 rows, 8 columns. Okay, and then I set A12 to be 5, A37 to be -8, and A54 to be 12. Okay, and now I got it AS to be a sparse version of the matrix A. And now have a look at the so now let me run this one real quick, and I'll show you the difference in terms of memory. So now let me clear everything first. Yeah. Okay, and then now we run this, and you see that the matrix A, okay, is a full matrix, and AS is a sparse matrix. And now look at the memories. So you see the sparse matrix, you use only 120 bytes, okay, but the full matrix is 448 bytes. So you see that there is a big difference if the sparse matrix, if the size is bigger, you see that it saves a lot of memories. Okay, so sparse matrix is only when you have so many zeros entries, but you have very few non-zero entries, then we call it a sparse matrix. And Matlab has a special commands for you to handle that. Okay, so I guess that is the best we can do. We cannot do question 5. Well, question 5 you can use the diagonal commands again, you know, so enter the script, sorry, write a script, you enter the values n, and you create a tri-diagonal matrix. So this one, you can try to do this. Try to use the sum command to complete this infinite series and print out, you know, so play around with this. And then I can post the solution after the labs. Yeah. So any question? Maybe let me stop the recording so then you can ask question if you want to. So